So what's wrong here? You see what's wrong here? See a problem? Yeah, okay, that's better. Okay, so we're going to talk about local search today. You know, we fix the problems as we see them. Okay, that's the idea, so local search. Just in honor of your project, or in honor of the time you'll be spending on this project, I thought I'd tell you a little bit about how mostly I'm trying to get some intuition on why is 3-sat hard? It's like, sometimes we present these things like a mystery. Oh, look, matching is easy, but 3D matching is hard. MST is easy, but TSP is hard. So it seems like a mystery. But let me try to give you these examples, and then maybe you can see why at least the algorithms we think about don't work. Okay? So, and these are examples. In fact, that's the whole thing, right? These complexity theorists have not been sitting around doing nothing. They didn't just prove a reduction and say, okay, we give up, it's hard. They think about why it's hard. And these are constructions that they came up with over the years to say, here's why. You know, here's some intuition as to why it's hard. And it's mathematical intuition. Okay, and we're going to talk about primality testing. So local improvement is what we just saw. Local search or local improvement is to find, you want to find a solution, any solution to your problem, make a local change to the solution, and then you check the cost. This is a way to address finding the optimal TSP or the optimal vertex cover. You just have a vertex cover that covers all your vertices, and then you start changing choices, making choices about what to do. So here's an example for the traveling salesman problem. You switch edges A, B, C, D to A, C, B, D. So let's look at what that means. Okay, so you have a tour that goes from V1 and then it comes back to V1. That's why it's a tour, right? It's a cycle. In some sense, there's the edge AB in the middle of the tour. You went from A to B, and in the middle of the tour somewhere you went from C to D. Okay, so to make it a little bit easier, let's take all these dots and make them S1, and you know, append the V1 there, and then take AB, and then S2 is those dots between B and C. Okay, it's just a set of cities there in the tour. Does that make sense? Okay, to CD. Okay, so now what it means is a switch is what we're going to do is, oh, we see that, you know, this pair of edges is cheaper than that pair of edges. The cost of AB plus the cost of CD is somehow larger than the cost of AC plus the cost of BD. Okay? So what I'm going to do is I'm going to make a new tour where I'm using these two edges in place of where AB and CD are replaced by AC and BD. And this tour should be cheaper. Okay? And now, if you have to do it, if you actually think about what you're doing is this C, this S2 in the middle actually goes from B to C in this way. But here you're going from C to B, so you need to reverse those cities. Okay? So that's just the splicing you need to do. Okay, so pictorially, you can think about this graph. Let's think about the metric being distance in the plane. Okay? Do you see two edges that might be more expensive than they could be? Does everybody see a way to two edges? Could this be AB and CD? Do you see two edges we could replace that with? Right. Okay, so we want to switch out these edges, so we pull them out. Now we have two pieces, and we switch them, and now the tour looks like that, right? Because these edges are more expensive than these edges, right? So even local search is even a little bit subtle, right? You can't just move one edge around for the TSP tour. You have to think a little bit about what your neighborhood is. Okay, so the neighborhood of your local search for this particular local search algorithm is all the pairs of edges, switches between two pairs of edges. When you take a pair of edges, and then you think about the other way of arranging them. Okay? Okay, so that's local search. Here's another example, which is graph partitioning. Okay, so So what we want to do is we're given a graph, and we want to split it up into two equal-sized pieces, exactly balanced, right? Because we're computer scientists, we want to do divide and conquer, so we want to divide it exactly in two, right? Then it's really easy to solve the recursion, okay? Although we can do it other ways, but let's just say that's the problem, okay? And we want to minimize the number of edges in the cut, okay? So this is motivated by many things, clustering, community detection. It used to be, when I write papers on this particular problem, I would always say this has a multitude of applications, blah, 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 and I would have many paragraphs. But back then, I think when I first was doing it, it was about laying out circuits on a chip across boards, splitting up the circuit so it could be divided among different chips or different boards. You want as few wires to go between the boards as possible. Okay, and so you want to minimize this expression, the size of this expression. Okay, so now local moves is here we have something, we have a graph, and it's easy to see what you want to do here, right? Can I just move one of the vertices over? I cannot, because the balance has to stay the same, right? I said here, one of the conditions, one of the feasibility constraints, you'll be doing this in your project when you do get to that part of your project. But the feasibility constraint says, no, these two sides need to be exactly balanced. So if I move this guy over here, that seems good because I reduce the number of edges in the cut. And right now this guy contributes 2, and now we're going to contribute 1, right? So that seems to improve the cut size. But now it's no longer feasible in the sense that the two sides are not balanced. Okay, so what should we do? Yeah, it says swap. I think you can read. Good. Okay, so those are the bad parts. We can swap them, and now we went from 3 to 2. Yay. Okay, not many theorems to prove here, but that's the idea. Okay, so again, when you have a problem, you need to understand what the solutions look like. You need to understand how to go from one solution to another, right? So with the TSP, we needed 2 edges to be switched. Here we needed to swap because I had this other condition that was hanging around. If I didn't have this other condition, what would I do? It's an interesting condition. Let me tell you, it is, right? What could I do? What would the solution be? Yeah, we put them all on one side, and then we'd have cut 0 edges, right? So it's a trivial problem at that point, okay? Okay, so, this is actually pretty good. I know in the past, the last time I taught this course, which was a while, there's a lot of good attempts that used local search. I think in between, people said these, yeah. What do you mean? Okay, I'm assuming I have a partition of the graph with some of the nodes over here and some of the nodes over here. And then I notice this pair of nodes. And I notice that if I switch this pair of nodes, the number of edges decreases across the cut. So that's all I'm doing. Yeah, this is a picture, but in a computer, you just have you have the set of nodes in one side and then the set L and R, and you have 2 hash maps or something. And then you pick 2 nodes and you pull one out of one hash map and one out of the other and then move them to the other side. And then you're right. You want to then do this calculation here, like what is the improvement, right? You want to say, well, I cut 2 edges now, but I no longer cut 3 edges now, so I've improved by -1. Okay? It's just a picture, but there's some data structure. I mean, the computer doesn't get to see pictures; it just has data structures, right? But yeah. Okay, so this is a good way. The techniques that were in my thesis. Local search would pretty much blow them away until I worked really hard to construct examples where local search didn't blow them away, or once you got big enough, then those techniques work better. So, and they have theorems that says those are approximation algorithms. Okay, why is 2SAT easy? Okay, so now this is the whole thing. I'm trying to get at what is this mystery? Why is 2SAT so easy and 3SAT so hard? Okay. Okay, so before we get into it, let's just remember the jargon. When I'm going to use the words variables, literals, and clauses. Okay, everybody remember a variable is that, a literal is either a variable or a negated version of it, and a clause is that. Okay, so there's a complexity view of why it's hard, and that's sort of what we've been working with the past week or two, is 3SAT can encode the operation of a computer, essentially. That's what it says, right? That's what Professor Chiesa showed you. He showed you how you can reduce from, you can take the verification program for any search problem or NP problem, and you can re-express it as the execution of that program on a computer on that input, okay? That are on the input. And then all you need to do is figure out how to set the inputs to make the program say yes, okay? 3SAT, we don't know. It can't, it's just not powerful enough. So this is just intuition. This is not formal. I haven't proven to you that 2SAT can't encode the operation of a computer. But it's sort of intuitively, we don't know how to do it, okay? And if we did, then 2SAT would be NP complete, and P would equal NP, okay? So now there's an algorithmicist view, which is 2SAT has an algorithm. That's why it's easy, okay? And here's the algorithm. You assign a value to a variable, and you can see why it's easy. You can get real intuition as to why it's easy. You assign a value to a variable. Now, you think about all the clauses that variable is in. Okay, so if the clause is, say you assign the variable to true, and the clause has the non-negated version of the variable, okay? That clause is true. What can you do with that clause? Throw it out. You don't need to worry about it anymore. It's true. Okay, and then there's also some clauses where it's negated. What do you need to happen? What needs to happen there? The other literal has to be true, right? So either way, for each of these clauses, you're making real progress. From one decision, it's forcing you into another decision, or it's just fine, right? Does that make sense? For each clause, it's either just fine, or it's forcing a decision on another variable. Okay? Does that make sense? Very clear, this is easy. And it's very local. Okay? Okay. 3SAT doesn't. Okay, and this is, again, is intuition. It's not a formal. This is formal, the first part. The formal part for algorithms is the one we have the algorithm for. The formal part for the complexity view is the one we have the lower bound for, the reduction for. Okay? So you assign a value to a variable. Each clause is either satisfied or drops to two literals. And now you don't really know, one of these two literals needs to be true, but you don't know which one, right? So you may have made progress. It's not clear. You can't do anything for sure, right? So this is variable assignment makes progress for either type of clause for 2SAT, but not for 3SAT, okay? Okay, so this is probably where they were in the 70s and 80s when they said, oh, okay, well, this is why this is this view, right? But subsequently, they're like, okay, well, let's think a little more about this. Let's make an instance, and this is what you're doing now, so you should pay attention. You should construct a 3SAT formula on n variables, and here's how we're going to do it. And I'm going to argue this is going to be a hard one for us to figure out, okay? So you randomly choose 6 n clauses, right? So pick 3 random literals. That's all we're doing. We're picking 3 random variables and random whether they're negated or not. That's a clause. Then we pick another one, and then another one, and then another one. And we keep doing this. Okay, we do this 6n times. Okay, the theorem says with high probability, this random instance is unsatisfiable. Okay? So what does your algorithm need to do if this theorem is true? It needs to prove to me that this is unsatisfiable, right? Okay. So now already you're thinking, well, how do I even do that? How do I prove it's not satisfiable? already a problem. Okay? So, I mean, in TwoSat, it's easy because there's a cycle, and you can detect a cycle or something in some associated graph. I think that's your homework. But, okay, so with high probability, random instances is unsatisfiable. So let's prove this theorem. Okay? So let's consider an assignment, just one, of true, false to our variables. Now, what's the probability? Now, it's just one assignment. So now if I take one of my random clauses, what's the probability that it's true? Well, only one of the, all of the literals have to be false for it not to be true. Right? All the literals have to be assigned false. Is that clear? So you can just evaluate that, and you see that, well, there's 3 literals. Each one is assigned false with probability 1/2. So they're all assigned false with probability 1/2 cubed. 1/2 times 1/2 times 1/2. So the probability that it's not satisfiable is 1/8. And you know, probabilities tend to add up to 1. That was a joke. So you get 1 minus 1/8, which is 7/8. So the probability that this clause is satisfied is 7/8. Okay? Does that make sense? Okay, now what's the probability that all the clauses are satisfied by this one assignment? Well, they're all independent. I mean, they're sort of independent. This is like an approximate calculation, but they're roughly 7/8 to the 6n, right? Because there's 6n of them. What's the probability all of them are satisfiable? It's 7/8 to the 6n. Okay? And now 7/8 to the 6th is less than 1/2. That's what I'm putting out here. I pulled the 6 out of the exponent. I said that 7/8, I put it into Python, 7/8 to the 0.6, and I saw that it was 0.44. Okay. Okay, so what's the number of assignments? 2 to the n. Okay, so this is the probability this one assignment satisfies all the clauses. It's not very big, 0.45 to the n. Really, really small. Okay? And the number of assignments are 2 to the n. So what's the probability? Now we can use the union bound. What's the probability that any assignment is valid for all the clauses? Well, for any one assignment, the probability is 0.45 times to the n, and there's 2 to the n assignments. So the probability that any assignment is valid for this set of clauses is 0.45 to the n, is at most, this is the union bound, it's a union of these events. Is a union meaning you want to, yeah, it's a or. It's the or this assignment or this assignment or this assignment or this assignment. So the probability that any one of it is at most the number of assignments times the probability of any one of them satisfying the clauses. So it's 0.45 to the n times 2 to the n, which is less than 0.9 to the n. So is 0.9 a small number? 0.9 to the n, is that a small number? Yeah, it's extremely small, right? Because it's less than 1 and you're raising it to some big value. Right. Okay, so this is the proof. So it says, with very high probability, there's no good solution here. Okay? Now you should be thinking, how should I generate something that kind of looks like this, but has a solution? Yeah. So you think about that. That's what you should be doing for your homework, okay? Or for your project, okay? Does that make sense? I mean, I could tell you, but it's more fun this way, right? Okay. You sort of want to do the same sort of thing, but you want to make sure there is an actual assignment, okay? Do some sort of random construction where you know the assignment and nobody else does. It's like a super secret. This is what you want to do for your instance generation, right? Yeah. Yeah. Okay, so this particular instance, what are you supposed to do? What are you guys doing this week? Have you guys started who started the project? Okay, good. Okay, so what you're supposed to try to come up with instances that you know the solution to, but I don't. Okay, this instance doesn't really work for that because there is no solution, right? So you want to figure out how to do the same sort of thing where you know a solution, but it would probably be hard for other people to come up with it. Okay? So you have what is called a planted solution, right? So this is what you want to be doing this next week or so. That's why I added this to the lectures. Okay? Okay, so now let's think about why this is hard from an algorithm. Now, I think this bears a little more study as a real algorithms nerd. Okay, so why is this instance? Why is it hard to come up with an algorithm for? Right, we have these algorithms. We have branch and bound. We have local search. What would they do on such a system? Okay, so with high probability. We know from before, with high probability, this instance is unsatisfiable. We also know any subset of n over 10 variables, if you look at just those variables and look at the clauses on them, most of the clauses don't have both endpoints in the many endpoints in that subset. It really looks like a tree if you look at the induced subgraph. Very, very few clauses have all of their endpoints inside of any subset. And this is true for any subset. Now, the proof of that is a little bit hard, but it's, again, just one of these counting arguments that you just saw me do. It's a little bit more complicated, but it's sort of you do some calculations, you enumerate all the subsets, you multiply things together using the union bound, and then boom. You see that, if you have a small subset, I mean, the basic idea of the calculation is the probability that all three endpoints fall in that subset is not very high, right? Because it's only 1/10. So that's the idea. Okay, and so it looks like this. So you have some huge number of variables, any huge number of variables where it's n over 10, and you don't know anything. Like they're completely solvable. Inside of here, almost any assignment works in here. Okay, so you don't know anything. So overall, there's no global assignment, but for any large number of variables, it's easy to assign. Okay? So this is a problem. So any reasonable size subset is easy to satisfy. So this is not satisfiable. So you're getting absolutely no guidance that this is not satisfiable, even looking at large sets of these variables. Every large set. Okay? So there's lots of satisfying. Not only are these satisfiable, in fact, there's lots of satisfying assignments for any large set. Okay, so you would when you use this backtracking algorithm, you don't know anything. When you start assigning variables, you're going to assign the variables in all the possible ways before you get any information. Okay, and if you want to use local improve, the landscape is flat. At some point, you'll do some local improve, and the local improve obviously is to try to satisfy as many clauses as you can, and there's lots of local minimums. And then any change of and there it's easy. Here, you just flip the variable to see which one, whether true or false, satisfies more clauses, right? That's the local improve algorithm. So basically, you'll get to a place where every flip does nothing. It just makes it even. Okay? Okay, so this is the notion of hardness. And there's real theorems to prove here, too, right? That the large subsets are all satisfiable. This is why it's hard. Every algorithm I know sort of has some, I used to say there's only two algorithms. You try the obvious thing, you try the obvious thing, or you try everything. Okay, so this, the obvious thing means that, you set a variable in toSet, the next one is clear what you're supposed to do. The ones in the clauses, right? And try everything is this exhaustive search, or if you like, the thing that's in between them is dynamic programming, where you sort of set up a table that tries some number of possibilities and tries just enough. But there's no dynamic programming there. Okay? Okay, so that's that. And so now we're going to go to modular arithmetic because we're going to talk about primality testing. Was that a hiss, really? Really? My eyes are glassy with how much I love it. So not mostly because it makes really nice questions on the exams. Sorry, didn't want to trigger any PTSD. Okay, we're going to do some review of modular exponentiation. We're going to so say that inverses exist and extended Euclid, where we're going to point to it. I'm going to do the modular exponentiation a bit carefully, just so you page back in the whole notion. You've probably seen it before, but I want you to page back in what modular arithmetic is doing, okay? Inverses exist. I'll quickly go over that. Fermat, I'll prove it, and then I'll get to primality testing. Okay, so I'm just going to set up my timer here. Okay. Okay, so computing x to the y mod z. Okay, this is fine. X, y, and z are n-bit numbers. Okay, we're in this range. We're no longer just doing math. We're actually doing complexity. So we're going to define the size of the numbers. Then the result is an n-bit number, plus or minus 1. Modular multiplication, a times b mod z. We can do that. You get c. And you can do this particular operation in n squared times, or faster if you want to do Karatsuba. Yeah, so what you do is you multiply by a to do this modular arithmetic. You multiply a by b to get c, and then you divide c by z, and you output the remainder. Okay, remember this? Okay, so mod z is just the remainder. You take the long division. Long division, you could do in order n squared. Okay, addition, you can do in order n. Now, x to the y, you can do this. How might you compute x to the y? You can multiply x times that, you make a loop, right? For I equals 1 to y, multiply the result times x, right? You start out with the result being x, right? Does that make sense? That'll approximately compute x to the y. So that's y minus 1 modular multiplications, where each one takes O of n squared. So that's exponential. Why is that exponential? Why does that take a long time? Yeah. Yeah. Why is n bits long? Okay, this is one thing that really you have to be careful about, right? I think we talked about it a little bit in 70, but it's unacceptable to not know it now. Okay, in 1.7, because that's the first lecture. Right? We talk a lot about the fact that the value of a number is not the same as the number of bits. Size matters. We're not using Roman numbers anymore. Right? So y is n bits. So y minus 1 could be theta of 2 to the n. Right? You could represent very large numbers with n bits. So this is a very expensive algorithm. Okay, so can we do better? So how might we compute this? So the previous algorithm just says multiplies 213 together 86 times. Okay, but you can notice something else, that 213 is 1 plus 2 plus 4 plus 16 plus 64, right? 87 is the sum of those things in the exponent. Does everybody see that? Or maybe you don't have to check the calculation, but you can write it down. What's special about those numbers in the exponent? The powers of 2, right? It's really the bit representation of 87 in some sense, right? The 64 tells you you're 1 in the 64th place, you're 0 in the 32 place, you're 1 in the 16th place, and so on. It's just like the decimal system, it's just binary. Okay, so now you can say 2 to the 87 is 2 to the 13 to the 1 times 2 to the 13 squared, and so on, right? Because that's just how exponents work. Okay, so this is also that. And so now the trick here is 2 to the 13. That's easy. I can compute that. There's only 7, at most 7 terms when I do this, right? The number of bits. If I write these out as things whose exponent is powers of 2, there's only n of them at most, n multiplicants, when you have n bits or 7 bits here, and there's less than 7 factors here. Okay, so now one other thing you notice is that 213 is 213 to the 1 is pretty easy to compute. 213 squared is pretty easy to compute. You just square the previous one. 213 to the 4, you can compute two ways. You can multiply 213 times 213 times 213 times 2, but you don't need to. You could just square 213 squared. Okay, and so on. Okay, so to compute the powers, you only needed the number of bits sort of multiplications, right? And now, this would not work if you didn't do it mod n. If you did mod 900, what would happen if you did it not mod 900? It would be huge. This would be a huge number. But if you mod out, it's only in the range up to 900. Okay, so this trick is not very useful for regular numbers. Okay, and now you say, so the total thing is it's to order the number of bits modular multiplication. Is that clear? Okay, so in general, you write y in binary, you can compute these powers, x to the 1, x squared, x to the 4th, x to the 2 to the n, and then you multiply at most n bar products according to the set bit positions in y. So it's O of n multiplications of n bit numbers, each in time O of n squared, so the total time is n cubed. So you can do exponentiation quickly by repeated squaring. Modular, when I say modular exponentiation, almost your reaction to say, oh, repeated squaring. You know, it's just the algorithm. So you can also, you don't have to do it this way. This is just some description of it, but you can code it up cleverly, right? We all took 61A. So if y equals 1, you just return x. Otherwise, you take r equals x to the y over 2, right? How is this computing that? We're using the magic of recursion. Then we square it, right? We square this result. That's what we're doing here. And then if it's odd, this is where we're checking the bit, right? Whether we should multiply it in or not. Okay, if it's odd, you multiply it in. If not, you don't multiply in this last one. Okay. So it's fairly straightforward. Okay. Okay, so right, V is just this subroutine. So yeah. Okay. Okay, so that all right. Now, what is division in modular division? What is the division? How do I divide by 5? We saw this before. You want to multiply by 1/5, right? Is that what you want to do? Multiply by 1/5? Well, you want to multiply 1/5 in the rationals is just a multiplicative inverse of 5. Okay, the number you get, you multiply 5 by to get 1. So what is division in modular arithmetic? It's not. You don't have 1/5 in modular arithmetic, right? You don't have that object at all. So. But we can say what it means sort of abstractly. It's the multiplicative inverse of a number is the number you multiply that number by to get 1. Okay? And 1 is a multiplicative identity in the rationals. So division is really, there is no division in modular division. Modular division is really just multiplying by the inverse. Okay? So here's why you divide. Here's one reason why you divide. 5 times y equals 7. What would you do to solve it if the mod 11 wasn't there? You would just multiply both sides by 1/5. Here, if you want to find y. Okay. So here, what is the multiplicative inverse of 5? Okay, so now I want to know is what do I need to multiply 5 by to get 1? Okay, so in the rationals, I multiply by 1/5. And I would get 1/5 times 5, and that's 1. Here, I want to say, what is x, where when I multiply 5 times x, I get 1. I don't know, what is it? Right, 9 works, right? So 9 times 5 is 45. 45 is equal to 1 mod 11. Does everybody see that? Okay, so now what I'm claiming is now that I know that 9 is a multiplicative inverse of 5, I can solve that equation by multiplying both sides by 9 and reducing mod 11. Now let's see if that's true. So x equals 9. Now what's y? Okay, the first one is I'm writing this equation again, 5y equals 7, and then I'm multiplying both sides of that equation by 9, right? Just as you would in the rational. So that's 63, which is equal to 8 mod 11, and that's y, right? Because 9 times 5 is 1, and that's y. Now, I wrote these symbols, I just wrote them down. Is it true? Is that actually the solution? So what did we do in grade school? We plugged back in. So we checked in, 5 times y. So now I'm plugging this 8 back into that equation and checking, and that equals a 7 mod 11, right? Because 11 times 3 is 33, 40 minus 33 is 7. Okay, so there are these things called multiplicative inverses in modular arithmetic. Sometimes. What's the inverse of 4 mod 6? What's, 3. He made a joke that nobody thought was funny. So we have many things in common. So there is no inverse of 4 mod 6. That was his joke, okay? Why isn't there an inverse 4 mod 6? Anything you multiply 4 by is going to be even, right? And 1 is odd, right? 1 is also 7, is also 13 mod 6, right? So there's no way to multiply 4 by anything to get anything but an even number. And if it's going to stay even, there's no way it's going to be 1 mod 6, because anything that's 1 mod 6 will be odd, right? That's the intuition. 4j, or another way to say it, 4j is at least 2 away from 6k for any jk, or they're the same, right? Because they both have power, they both have factors of 2 in them. Okay, that's what I'm saying. They're both even. Anything mod 6 that's going to be 1 is going to be odd. Okay, and more particularly, they have a common divisor that's greater than 1. So the greatest common divisor of any 2 numbers, we talked about that a lot. It's just the largest number that divides them both. If GCD, if this greatest common divisor of 2 numbers is greater than or equal to 1, there's no inverse mod y, for x mod y. Okay, so GCD, if GCD of xy is equal to d and d is greater than 1, that says x has no multiplicative inverse mod y. And we can prove that. So ax equals 1 mod y. It's the same thing as saying, that's an equivalent statement to saying ax equals 1 plus by for some integer b. Right? That's because when you divide, that's all that dividing says, right? When you divide by y and get the remainder, it means there's a quotient, b, which corresponds to that division. There's a quotient in the remainder. Okay? So that's the same thing as ax minus by is equal to 1. Now we know that x and y both have d as a divisor. So we know we can write x as I times d, and we can write y as j times d. Right? And then this is the same argument we did before, but for evens. Now we just plug in, right? We're plugging into this blue equation. X is I times d, and b is j times d. I mean, y is j times d. And now, what can we do with this equation? You see something in both of these guys? Is there a d in both of these expressions? Yeah. So we should factor it out. So now we have 2 integers. This is an integer, and this is an integer. Right? All of these are integers. Okay, so when you multiply 2 integers together and get 1, what must they both be? 1. In particular, D better be 1, right? Which implies that D must be a factor of 1, and that is the only factor of 1 is 1. Right? Okay, so that says, I mean, but really it says this. It says if I want to, if there's, you know, I can't, if my steps are too long, and the steps are really in units of the multiple, of the common multiplier, I can't get to something in between the steps. Right? Okay. Okay, so extended GCD finds an A and B where AX plus BY equals D, which is equal to GCD of XY. Now let's say we have integers A and B where AX plus BY is equal to 1. What is the greatest common divisor of X and Y? I have an X and Y, this if statement here. AX plus BY is equal to 1. What's the greatest common divisor of X and Y? 1, right? It says you can find it for the GCD. Okay. Now, what is the multiplicative inverse of X mod Y? Just trying to... Anybody? What do you think it is? Yeah. Is it A? Is it B? Or is it Y? Yeah, just like we have one fact. AX plus BY equals 1. Look at that fact. Okay? And now put a mod Y next to it. Right? If you put a mod Y next to it, what is Y? Mod Y? 0. And then what do you get? AX equals 1, right? So I got one equation. AX plus BY equals 1. I had it on the slides. I want you to do it in your head, right? And Y equals 0 mod Y, right? So you get A, if you take this equation mod Y, this Y becomes a 0, and you get AX equals 1, right? So what's the multiplicative of inverse of X? A. Okay, so we sort of quickly went through material, modular arithmetic, and okay, let me give you a break. Okay, so let's get started again. Okay. All right, so we're gonna remember what happens when you have an expression like this: x times y, and then you multiply by u, and then you multiply by v. Remember what happens if you keep doing that, x times y may be bigger than z, right? And when you're doing these calculations, if you do a big long sequence of these and you just let it go bigger and bigger, there's a problem. It just blows out, right? It's not good. So after you multiply x times y, what you should do is bring it back into find the remainder divided by z, right? So you want to reduce each intermediate result mod z, right? When you did this on your homework, that's what you would do, hopefully. Now, this notion of reducing exponents and many other things, the basis of RSA, was this theorem called Fermat's theorem. And it says for a prime, p, and any number between any number that's essentially not 0 mod p, a to the p minus 1 is equal to 1 mod p. Okay? Does everybody remember the proof? Okay, well, we'll go over it again. But in some sense, this is already useful because now you can, who wants to do 3 to the 25 mod 7? What's the answer here? What is 3 to the 25 mod 7? Okay, so basically what the Fermat's theorem says is 3 to the p minus 1. Here p is 7, right? That's everybody's favorite prime is 7. P is 7, so p minus 1 is 6. So we know that 3 to the 6 is 1. So 3 to the 24 is 1. So 3 to the 24 is 1, and we have one more 3, right? In my head. And I'm old, and I can't do this anymore. So, right? But it makes it easier, right? These calculations become easier. It's B or 3. Okay, so now let's prove Fermat's theorem. Okay. So what are those? Those are all the elements, the non-zero elements of ZP. If ZP scares you, it's just 0 to P minus 1. It's all the ones, it's just the things that are mod P. Okay? Okay, what do we do with them? Yeah, we have one other thing here. There's a P and there's an A, so we should better do something with the A, I suppose. So what we're going to do is we're going to consider the set. We have the set T, and we're going to consider another set where for each element of T, we're going to multiply it by A. Okay, so it's the set I'm writing in shorthand. Maybe I should have written it out. I should have maybe written A times 1, comma A times 2, comma A times 3, or it's a little easier to write it 1A, 2A, 3A, up to P minus 1A. Okay, that's what S is. What is S? S is T, okay? So let me, and I'm going to show you that, right? S is the same set as T, right? That's where we're going. How are we going to prove that? Okay, first we're going to say, how big is S? Well, how many elements are there in the domain? This is a function, and we're taking all these inputs, right? All the elements of T as our input. How big are the elements in T? P minus 1, or the size of T, which is P minus 1. Okay? So, and now that's what the inputs are, but now that's not what's actually in S. It's A times every element in T, right? It could be that they all go to the same image, right? But since A has an inverse, the image is the size of the domain. Every element in the domain goes to a different image. Otherwise, you can't have inverses, right? If two guys go to the same element, it doesn't make sense to have an inverse. You have two pre-images, okay? So S is the same size as T, right? Now, what's the relationship between S and T? Well, the elements of S are a subset of the elements of T because you're working mod P. The only elements there are 0 to the P. And you can't get 0 here. Okay, so you only get elements when you multiply, because 0 doesn't have a, you can't divide by, if you multiply by the multiplicative inverse of A times 0, you'll get 0 again. You won't get 1 through P minus 1. Okay? So it's a subset. So therefore they're the same. If S is the same size as T, and S is a subset of T, then S must be T. Okay? So now what should we do? We have two sets, they're the same, but one has all these A's in it, and we're trying to build some expression with A, right? So what we do is if they're the same, let's multiply all the elements in both sets together. Okay, so we're just multiplying all the elements in T together, 1 times 2 up to P minus 1. Now all the ones in S, and multiply them together. And you get 1A times 2A plus times 3A, and so on. Okay, so we know that pi S, we can pull all these A's out, right? Because multiplication is commutative. Modular multiplication is commutative. So you get an A to the P minus 1, and you get a pi T. And now you also know that pi S is equal to what? If you multiply all the elements of T together and all the elements of S together, and they're the same set, what must they be? The same. So pi S is equal to pi T, right? So we also get that pi S is equal to this, and pi S is equal to pi T, so we get this is equal to this. Right? Okay. So now pi T has an inverse, right? Because it's a non-zero element between 1 and P minus 1. And so you can get rid of pi T. You can multiply by pi T inverse. You can divide out, and you get A to the P minus 1 is equal to 1 mod P. See, not so scary, right? In 70, it was not, people weren't too happy with the proof of Fermat's theorem, but now it's fine, right? Does that make sense? Okay. Okay. Okay, so there's something nice about primes. And we saw before in 70 that RSA relies on primes. So they're really nice. So what we want now is we want primes. And we're computer scientists, so we want big primes. Big is good. Big is good. Okay, how do I find one? Are there even any big primes? So there's lots. Many of them is 1 over log n for numbers with value n, or for a 100-digit number, about 1 in ln 10 to the log n, so 1 in 200. Okay? So I should do a demo so we can find some primes. So I'm going to find a prime. And I'm going to find a big prime, because no stinking small primes, right? Okay, let me see. Okay, so what it does is it finds a random integer with some number of some size in this range, right? That's what the first line does. Then it does this test. Is it prime? Okay, it's checking whether it's prime. And that's something we're going to go over how to do. Okay? So it's a 100-digit number, right? That's a 100-digit number, I guess. Okay? Is that 100 digits? Yeah. And how many primes do I want to find? How many times do I want to try? 200, right? That's what I said. I would hopefully find some primes. All right, 1 in 200 should be prime. That was terrible. What was my bug? So I found one, right? You can try again. Probably with a different seed. I need a different seed, but let's see if it is a different seed that I entered. Yeah, this time I found 2. It's about 1 in 200, right? So I tried 200 times. I tried 200 random numbers, and I checked when they were prime. Okay, so in some sense, this is really fast. How do I know that's prime? I can't tell if it's prime. Like, how would you tell if it's prime? Well, I divide it by 1. Okay, that would work. I would divide it by 2. That would say no. I'd divide it by 3. That would say no. And then I would do this until the square root of the number. Well, that's a disaster. That's 10 to the 50. That's not what it did, right? It did something else, right? So let's see what it did. Uh-oh. My computer is no longer happy. Oh, I know what the problem is. Okay. So, why is it not working? Okay. Why was the demo so fast, right? It shouldn't have been that fast. How could we tell whether a number was prime, right? It seems like you should be able to factor it if you can tell whether a number is prime. So the obvious is my thing wrong? Okay. So it take around 10 to the 50 steps. Did it take 10 to the 50 steps? No, my computer, that's an old laptop. It's not going to go that fast, right? It's 6 years old. Maybe now. Maybe your phone could do it, but no, it can't, right? That's too fast, right? More than the number of particles in the universe times the number of nanoseconds. It's the birth of the universe, right? It's really long. Okay, so let's think about 7. What is 2 to the 6 mod 7? So I'm going to tell you how we do it. It's going to use Fermat's theorem in a sense, but not really. Okay, what is 2 to the 6? It's 1, right? It's 1 because of Fermat. What about 3 to the 6 mod 7? What is that? 1. Well, we knew this, right? We didn't have to do this calculation. We just proved the darn theorem, right? So it's like, oh, yeah. Answer is A or 1. Okay. What about 3 to the 5th mod 6? I don't know. I don't care. Okay, so Fermat's theorem doesn't tell us, right? It doesn't tell us about this. It could be 1. It may not be 1. Okay? But what if we did that with a number? If we took 3 to the whatever mod to n and it wasn't 1, what would we know about n? It's not prime. That's a proof that something's not prime. Right? Really? Like the only proof I know that something's not prime is to factor it. But no, if it doesn't obey Fermat's theorem, it's not prime. Right? That is power. I can prove something is not prime without actually knowing its factor. Right? This is power. Right? Yeah, I don't care. Okay, so there's one thing. Okay, so if this is the okay, there's some special cases which are weird, okay, but they can be, the real primality tests filter them out, okay. There's something called a Carmichael number. It's a composite number, n, where a to the n minus 1 is equal to 1 for all n that are, for all n, if a is relatively prime to n, okay. So that's going to be, there are these numbers where essentially Fermat's test works for them, for every a. Okay, for every interesting a. Okay, so now what I'm going to say is not, for anybody that's not a Carmichael number, it's not just that one a doesn't obey this equality, it's half the a's don't obey this inequality, right? Okay, so let's go ahead, let's just retrace just a little bit and say, I want to prove something's not prime. Say, factor it. Okay, I can't do that. It takes too long, or we don't know how to do that. Okay? But if I find an a where a to the n minus 1 mod n is not 1, it's not prime. Okay, so now this says if there's any a where this is true, half the a's it's true for. So it's not like I have to search for all the a's. I only have to guess an a, and half the time I'll be right. Okay, so this is a powerful theorem. Right? It says that not only if there's any a where this equality is not satisfied, half the a's it's not satisfied. Okay, so now, and Fermat's theorem it says that for any a, this is satisfied if it's prime. So these are different. It says if it's not prime, half the a's I'm going to catch it. If I just try a random a with with probability of half, at least, this will fail this test. And I'll know it's not prime. I will catch it not being prime. You're not prime. I see you not being prime, right? But for any prime, it's going to always be right. It's going to say, fine, it's going to pass this test. Okay? So it's an approximate converse of Fermat's theorem, right? It says that it would be a pure converse if every a was not equal to 1, but that's not what it says. It fails for half of the a's. So it says prime, they look like this. Not prime, it mostly looks like this, or at least half of it looks like this. Okay. The rare exceptions are these Carmichael numbers, which can be fixed with a more complicated algorithm, but not much more complicated. I could have done that in another half hour. Okay, so given n and a, where n is n prime. So what do you do now? I'm not telling you whether it's prime. What would you do now? Do we know it's prime? I've checked it with a. I got a. I know a to n minus 1 is equal to 1. Is n prime? Is it prime? No? Not prime? It could be prime or composite. We don't know yet, right? It could have been prime. We don't know anything for sure here. What about this? What do we know about this one? If I find an n and an a where a to the n minus 1 is not equal to 1 mod n, is n prime? No, right? Okay, so now I'm saying it's not prime, so therefore it must be easy to factor. Is that true? Well, we rely on not knowing how to factor it, right? That's what cryptography is, right? So this is why this is kind of really neat, right? There's this structure, and you can tell if something is not, you know it's a composite. I know it's a composite, but I can't factor it, right? You can give me your public key and the end part of your public key, and I could test that it's composite. I could catch it being composite. I said, aha, you're composite, I caught you. But I can't factor it. Okay, so given n is not prime and not a Carmichael, how many a's are there where a to the n minus 1 is not equal to 1 mod n? At least one of them, at least half of them, all of them. Right. Well, okay, what we're going to do is actually prove that A implies B. All we need is one of them, and then I'm going to prove to you that half of them are. Okay? Yeah, and then the primality testing algorithm is fairly straightforward. You just repeat, okay, it's probabilistic. I lied a little bit. When I said that was prime, it's only prime with probability 1 and 2 to the 100, which is basically, for me, I'm willing to take that chance. Okay? With failure probability 1 to the 200. Okay, so if it passes every time, okay. If it passes here, I'll go. So this is the primality testing. If not, return false. If after 100 iterations through this loop, I never catch it not being prime, I just return true. I was like, okay, I give up. I'll trust that this is prime. Okay? I could make a mistake here, right? It could be that every time, all 100 times, I chose badly. I chose an A that actually worked for this composite number that passed this test. But let's see what the probability is. It passes the test once with probability at most 1/2. Okay. If it returns, in the case it returns false, we know for sure the thing is not prime. We found a proof that it wasn't prime. Okay. If it returns true, it passes the test 100 times. And the probability of passing a test 100 times is what? Which one of these? Yeah, they're independent. So every time you're picking a different A, or not a different A, but uniformly at random some A, and each time you have you only have half a chance of passing the test, the composite number. So it's 100 to 1/2 to the 100. Okay. Okay, so when I said that was prime, I might have been wrong. When my computer said that was prime, I might have been wrong, because I only checked 100 times. But the probability I'm wrong is 1/2 to the 100, and I'm willing to tolerate that. It's way less than the probability of me dying in the next minute, right? Like way less, like not close, right? Like I'm way more likely. I mean, it's pretty morbid, but right? Lightning could strike through the building with probability higher than that. It's essentially 0. Okay. Okay. So so what we're using is that that non-prime, non-Carmichael numbers, at least half the A's must fail the test. Right? There's this test. We take A, we exponentiate, that we can do efficiently. We did that with repeated squaring. We can check if it's equal to 1, that's easy. But what we started with is just saying that for anything that's not prime, only one A fails the test. Okay, so now I argued, but that by itself actually tells us half the A's fail the test. Okay? So if it says if there's even one A where the GCD of A and n is 1, where A to the n minus 1 is not equal to 1, then for at least half of them, A to the n minus 1 is not equal to 1. Okay? So that's the theorem we need to prove to finish this off. Okay, if you have one bad apple, one that fails the test, I'm using bad wrong here, but okay, this is not bad. Okay, so this one is, ignore the title. The title doesn't make sense. Okay, so Okay, we know this. The theorem says we have at least one A which fails this test. Okay, now I want to argue that half the A's fail this test. Okay, well, either maybe all of them fail this test, and then we're fine. If not, maybe there's one guy that passes the test, B. So B passes this test. It would fool our probability test if we used B. Okay, so but B to the n minus 1 is equal to 1 mod n. It kind of, if you used B as your example and took it to the p minus 1 or n minus 1 in this case, you would get 1 back and you would think maybe this could be prime. Okay? Okay. So we have this A, which is not equal to 1 when you exponentiate it, and you have B, which is equal to 1 when you exponentiate it. Okay? Now let's say for this B, if you get, let's multiply them together. Now you get a different number, A times B, which is A to the n minus 1 times to the, and now let's take this product and see whether it passes the test. Is it going to pass the test? No, right? Why not? What is B to the n minus 1? And we know that A to the n minus 1 is not equal to 1. Okay, so for any bad guy, what we can do, if we have a bad guy, we can multiply it by A, and what do we get? A times B, for any bad guy, A times B is what? A good guy. It fails the test. Okay, good and bad are sort of relative. All right, let's just say, if for any guy who passes the test, where B to the n minus 1 is equal to 1, anybody who passes the test, if I multiply by A times B is going to be an element that fails the test. Okay? Okay. So for every bad B, now here the bad is it passes the test, and A times B fails the test. So how many fail the test? At least as many as pass the test, right? For everybody who passes the test, there's at least one guy who fails the test, right? Right? AB fails the test if B passes. And now the final thing is A has an inverse mod n, because the GCD of A of n is equal to 1, and we talked about that. If the GCD of A of n is 1, then we have an inverse. So it's not like A times B1 is equal to A times B2. They're separate, they're different things, right? So A times X is mod n is 1 to 1. So for each bad B, AB is different and good, meaning that it fails the test. So at least as many good as bad, right? So at least half are good, QED, right? Okay, so this is, again, we're using inverses. The fact that A times it is a one-to-one function. And then we're using the fact that even if one of the guys, we're just using this one guy who's bad to make this function. And this function, what we're doing with this function, we're mapping the whole bad set to good elements. So we know that the bad set is mapped to this other set, which are all good. And that means, and it's a one-to-one function. So this good set is at least as large as the bad function. Yeah. You're taking all of them to be mod n. Yeah, he's asking about the range, but now you think that they could be mapped to the same number, but they can't because of this notion that A is relatively prime to B, so it's a function. A times X is a function. So he's actually sort of getting, he was slightly thrown off by AX is 1 to 1. That's the answer, right? He's saying, what if A times X, when you map it, A times X is maybe going to be larger than N, and when you put it back in the range between 0 to n, you think maybe these things can collide. And that's why we need to do all that work about these things being 1 to 1, right? Being relatively prime. Okay. Yeah, my high school math teacher, he would never use the box. He would say, quite excellently done. Did your high school teacher do that? No. No. Did anybody's high school teacher do that? Oh. I'm sad for you. Okay. Are exactly half good? Is that what we just proved? No, at least half are good. Okay. More than half could be. They could all be. Okay. So it correctly determines primality with failure probability 1/2 to the 100. If it's prime or Carmichael, it says it'll return prime. If it's not prime, it says it claims it's prime with probability 1/2 to the 100. Okay. Okay. So that's I think we're done a little early today.